Hello everyone. Today we're gonna learn about binary search algorithm. This is a simple search algorithm, yet very efficient. So this is a good one to start off our algorithm series. This tutorial is a part of the data structures and algorithm class. First, we're gonna look at a typical problem solved by binary search algorithm. But let's have a step back and understand why it's called binary search. Binary in this context means there are only two options, like 0 or 1, or left or right. Binary search is very performant because it drops half of the data points in every iteration, and we're gonna see how it does it in this example. So we are given a sorted array in increasing order, like 1, 2, 4, 7, 9, and so on. And we are asked to find an index of an element, in this case 65. The small thin number we see down here are the indexes of the number in the array. Now, remember, whenever you're given a problem, on top of everything, think about brute force solution first. Why brute force first? Because it's so easy to think about and implement. And we will quickly know the complexity of the brute force solution. If there is a brute force solution for our problem, the complexity of that brute force solution become an upper bound for any possible solutions. And then what we try to do later is to see if a more sophisticated algorithm will have a lower complexity compared to brute force solution. Now we're gonna apply that way of thinking to our problem here. For this problem that we have, we basically want to pick number 65 out of the array and then see what the index of 65 is. And with brute force, if we can list all the elements in the array, we're gonna be able to pick 65 if 65 is in the array. And that's gonna give us a for loop to pick out every single number in the array. The green numbers here are the number that we're gonna loop through. We're gonna go from 1, 2, 4, 7, 9, and so on until we hit 65. And then we return the index of 65, which is 13. And because we loop through everything, in the worst case scenario, our time complexity is O of n, with n is the number of the elements. Okay, so now we have a solution. Can we do better than O of n? And binary search say yes. So the way binary search works is, we're not gonna start at the beginning. We start at the middle. And because this is an array, we always know the leftmost index, which is 0, and the rightmost index, which is 14, the length of the array minus 1. And then we can calculate the middle index. It's the average of the leftmost and rightmost indexes. In this case, it's gonna be 7. And at index 7, we have the number of 23. Binary search takes advantage that this array is sorted. Because it's sorted in the increasing order, the element 23 we have here effectively divide the array into two parts, the left of 23 and the right of 23. And because the array is sorted, we know the left of 23 is always smaller than 23, and the right of 23 is always bigger than 23. And the number we're looking for, which is 65, must be in one of these options. In this case, it's in the right of 23. So in the next iteration, we're gonna totally ignore all the elements in the array on the left of 23. And we will only consider the numbers on the right of 23. And the next step we're gonna do is, we're gonna move the left pointer to 34, which is right next to 23, which has the index of 8. And then we're gonna recalculate the middle pointer index, which is the average of the new leftmost and rightmost, and that's gonna be 11. And the element at 11 is 59. 59 is still smaller than 65, the number what we're looking for. So we're gonna drop everything on the left of 59 and only consider the number on the right of 59. And that's gonna give us 60, 65, and 70. And as we do the same iteration, we found the number that we're looking for, 65. And it always converges at the middle index. So we can return the middle index, which is 13. As you can see for binary search, in every iteration, we drop half of the data points. For the first one, we drop this half, and the second one, we drop this half. And just like that, we already found the number that we need. So we actually only consider 23, 59, and 65. That is much faster than considering every single element in this array, like the brute force solution. And every time we see that we drop half of the data points, in each iteration like this, the time complexity is O log n. It's exponentially fast. And O log n is better than On. And that is how binary search works. It takes advantage of the sorted array to not visit unmeaningful data points. Next, Let's have a look at our binary search implementation. We are given a sorted array in increasing order. We're given a target number 65. And this is the implementation of our algorithm. First, we assume that the target number is not in the array. At the beginning, our left index is going to be 0, right index at the end of the array. And as long as left index is not greater than right index, we're going to calculate our middle index, print the indexes out, print the array elements out. If the array element at the middle index equal to the target number, we found what we need. We update the result, and we break out of the loop. If the array element at the middle index is smaller than the target number, we will continue to the data point on the right. And we do so by updating the left index to the middle index plus 1. If the array element at the middle index is greater than the target number, we will continue with the data point on the left. We do so by moving the right index to middle index minus 1. And we're gonna keep looping until left index is smaller than or equal to right index. After that, we're gonna return the result. And if we run our binary search, it will give us our result in only after 3 iterations. And the result is, the index of 65 is 13. For time complexity, binary search drop halves of the data point in each iteration, so the time complexity is O log n. Next, from our typical problem for binary search, we're gonna generalize the characteristic of problems that can be solved by binary search. And the problem that we usually see is searching for a number. And once the inputs of the problem had these characteristics, sorted array or balanced binary search tree or some sort of known direction, either increasing number or decreasing number, we can use binary search to solve the problem. And the time complexity is efficient O of log n. Wherever you see a search for a number, an input characteristic is known direction, increasing or decreasing, then you can use binary search for a good time complexity. Now we're gonna have a look at another example to see this in action. This time our problem is we are given an array like this one or this one, and we are asked to check an element and its double exists in the array. So let's say if we have 5 in the array and we have its double which is 10 in the array, we're gonna return true. And if we don't have 10 here, 2, 5, 3, 7 don't have any double of itself in this array, so we're gonna return false. Another example array is this one. Then we have minus 2, and double of it is minus 4, and they both exist in this array, so we're gonna return true. To start, we always think about brute force first. So if we really think about it, if we have all the combination of two numbers from this array, like this, 10, 2, 10, 5, 10, 3, and so on, we will be able to see if a number and its double is within the original array. So all possible combination of two numbers, that is two nested for loops, and that's gonna give us the complexity of O n squared. Now this is our benchmark. Can we do better than this? If we want to use binary search, we need to know some sort of direction. But there's no direction in this array. Then we actually can create the direction by sorting the array ourselves. Now the best sorting algorithm gonna take O n log n, and that's still better than O n squared. So we're gonna sort it first. And that's gonna give us 2, 3, 5, 7, 10. With step 2, we pick our first number with a for loop, which is 2 here. And step 3, we pick the second number with a binary search. So we're gonna do a binary search for the remaining numbers, which are 3, 5, 7, 10. And in this case, we search for 4, which is the double of 2. And we're gonna keep doing that for the rest of the array to see if we have any number and this double in the array. And in this case, we actually do. When the for loop got to 5, the binary search for 10 gonna return 10, and then we found our result, which is 510. So for this algorithm that we have here, we have a binary search nested in a for loop. So that's gonna give us O n log n time complexity. And big O of O n log n plus O n log n equal to O n log n. So finally, we have the complexity of our whole algorithm as O n log n, and that is better than O n squared. So with binary search, we have found a better solution than brute force solution. In summary, we quickly used brute force to find a solution, and use it as a benchmark. Then we sort the array because sorting still have better complexity than brute force of O(n) squared. Then we use a binary search nested in a for loop to find our result with a complexity of O(n) log n. And this is our implementation. We sort the array. We assume the double of the element does not exist. We pick the first number with for loop. We calculate the double. For example, 2, 4. We also need to calculate half because double of minus 2 is minus 4. Then we have our left indexed and right index. And we're gonna do our binary search here. To pick the second number, we calculate the middle index. We print the indexes out and the array elements out. And if the array element is the target that we're looking for, we change the result to true and we break the loop. Otherwise, we're gonna choose to continue looping either on the left or on the right. Then we finish the loop and we return the result. And if we run this, it's gonna return true. For time complexity, we have binary search nested in a for loop, so the time complexity is O(n) log n. Next, to summarize, we're gonna have our table of problems and solutions here. So it's easier for you to remember which problem along with the problem characteristic can be solved with what algorithm. And you will also know the time complexity of the algorithm. For example, if you want to find a truth, and the truth is you want to search for a number, and the input characteristics is you have sorted array or balanced binary search tree, then you can immediately think about binary search. And the time complexity is gonna be O log n. We will fill up our table with all the problem classes. And this table gonna act as a thinking map, where when you face a problem, you can categorize the problem and its subproblem. And when you see suitable problem characteristic matches with the algorithm, you immediately know what kind of algorithm you can use to solve this problem. After we're done with our algorithms, this table gonna act as a thinking map, where you can have solid information to reason upon and solve your problem. That is all for today's tutorial. Thank you for watching, and I will see you in the next video.